For the Day 20 pre-lecture video, I wanted to talk a little bit about torque, which is one of the first concepts or things that you're going to run into in Chapter 10. And I also wanted to take the opportunity to review with you the cross product and how we calculate it, especially for unit vectors. So in Chapter 10, we're introduced to the concept of torque. A torque is produced when a force acts and it causes a rotation of the object about a given axis. For us, torque could be thought of as the rotational equivalent to torque. We're going to use this Greek letter tau to denote torque. So when we first see torque, what we have is we have some sort of object that can rotate, and there's going to be some point about which the rotation will take place. That is going to be the axis. In this picture we have a hinge and we have this bar, and so of course the bar could rotate about the hinge. There's a force acting on the bar, and the way that it acts, it is going to cause a rotation. It's going to cause things to rotate about this way. The way that we calculate torque in terms of the magnitude of it is it's the magnitude of the distance from the axis of rotation to where the force acts, that's r, times the force times the sine of the angle between them. One of the things that we realize is that if we think about the force acting along this direction, we realize that this is F sine theta, which makes sense because it's only that perpendicular component of the force which is going to cause the rotation. The parallel component, F cosine theta, would actually act all the way through the hinge, and if we pull in that direction, there's not going to be any sort of rotation. And so this is the first time that we're introduced to how we calculate torque. The unit of torque is going to be Newton meters. But you notice that I use notation to indicate that torque is a vector. Torque is a vector, and so it has to have a direction. In a very similar way to how our angular quantities we found last week, their direction was along the axis of rotation. The same thing is true about torque. And so the direction of the torque would be along this hinge. So torque, we find, is RF sine of theta, and this is when we're just talking about magnitude. So we just looked at that definition of how to calculate the magnitude of the torque previously. And if we remember from way back when we did Chapter 1, we were introduced to two operations that you could do with vectors. One was the dot product and the other one was the cross product. We saw that the dot product could be used to calculate work. This is going to be the first time that we're going to see how we could use the cross product. Remember that by definition, the cross product, and the reason we call it the cross product is because we use this symbol for the operation, and the magnitude of the cross product is the magnitude of these two vectors times the sine of the angle between them. So you can see from the similarities that torque could be actually calculated as R cross F. One of the things that we want to remember is it's pretty important when we use the cross product is not commutative. We cannot write this. This is not equal to F cross R. You actually would introduce a negative sign. So that's why we say it's not commutative. The other thing is that I mentioned earlier in the last slide is that, of course, it's a vector. The direction of the torque vector is going to be along the axis of rotation, so it's going to be along the hinge. We use the right-hand rule, or we could think about the direction of the rotation. And if we curl our fingers in the direction of the rotation, our thumb is going to point out of the page, and this is going to be the direction of the torque. It's along that axis, and that's the direction. So another interesting thing about torque that also is true about the cross product in general is that any two vectors can define a plane in space. Basically, the way that we could sort of think about that is I can always draw two vectors on a piece of paper. That paper then becomes the plane that those two vectors lie in. According to the right-hand rule that we're going to talk about a little bit more in class, when we take the cross product of two vectors, the product is perpendicular to the plane that they lie in. And so, as we saw on the previous slide, the torque vector pointed out of the page. This is the way that we show out of the page. I like you to think of it as an arrow, and when it's coming out at you, we see the point of the arrow. If it was going into the page, we would see the feathers of the arrow, and we draw it like this with a cross. So, torque, the vector, or anytime we take the cross product of two vectors, the product is perpendicular to those two vectors that we took the cross product of. And we use the right-hand rule, which we will talk about in class, because I'm not going to show you here. But another thing that I wanted to remind you of is how do we find the cross product? So the cross product, when we find, I know I did the definition, but what I'm interested in is what if I have two vectors written in unit vector form? How do we find the cross product? And I hope that you remember, I did do a video on this, but I want to show you again, is we use the matrix method. Now, we're going to form a 3x3 matrix. The top row is going to be our unit vectors. The next row is the first vector. That'll be the components of vector A. The x component goes here, the y component goes here, and the z component goes here. Then finally, the third row is for the second vector. It's the x component, the y component, and the z component. Then what we do is we're going to expand about this row, which means that we're going to take each one of these terms and each one of these unit vectors will be multiplied by the determinant of a 2x2 matrix, which does not include the row or column that unit vector lies in. So let's see what we mean by that. For I, I've already drawn the row and column that we eliminate. We would be left with 4, 0, -5, and 0. The j, remember for the j term we have a minus sign there. We eliminate the row and column that j lies in. We're left with 3, 0, 4, and 0. And finally we have k, and we eliminate the row and column that k lies in. We get 3, 4, 4, and -5. And then the way that we find these are determinants. Remember, you take these two terms, you multiply them by each other, then you subtract the multiplication of these two terms. That's how we do it. So for A cross B, for the I term, we get 4 times 0 minus a -5 times 0. For the j term, we'd get 3 times 0 minus 4 times 0. And then for the k term, we get 3 times -5 minus 4 times 4. So, what's going to happen is, of course, these two terms are 0. We're going to talk about why we should expect that. And for A cross B is going to be in the k direction. It's going to be equal to -15, -16. So that's going to be minus 31. Okay. Now, I said a minute ago that we should have expected that this product was going to be in the z direction. And the reason that that should be expected is because these two vectors, these lie in the xy plane, because they only have x and y components. And so remember what we said about the cross product, or the vector product. The first two vectors that you're taking the cross product of define the plane, and then the cross product is perpendicular to that plane. And that's what we saw with this answer.